Welcome back to the Dark Matter podcast. Today is a bit of a special episode. First of all, because this is the last of season 1. So thank you in the name of the whole team for tagging along with us on this space journey. The other reason is that today I'm welcoming not one, but 2 guests, as you can see, in person as well. So thank you so much for coming out. Germain Garreau, you are a PhD student at the Institute of Astronomy at KU Leuven, here in Belgium. And Kaustubh Hakim, you are an astrophysicist and an geoscientist. So we'll go back to that word. And you have a double affiliation with the University of Leuven and the Royal Observatory of Belgium. Both of you, welcome and thank you for coming.
Well, thank you.
Thank you.
My pleasure, really. So first, I'd like to turn to you, Germain, to ask about your research. So you are an optical engineer by training, but now you're doing your PhD, which you started a little bit over a year ago, on the detection of exoplanets. So that seems like quite a stretch. I'll ask also some question about this. But essentially, you're working on the design of optical instruments to detect and image exoplanets. So my question is, first of all, what is an exoplanet? And what is the difference between detecting them and imaging them?
Yes, that's an important difference. But so first, what is an exoplanet? I get this question very often, but the answer is very simple. This is a planet just like the one we have around the solar system. So just like the Earth, Mars, or Jupiter, for example, the one we see on the night sky. These are exactly the same. These are other planets orbiting other stars than the sun. And so we call them exoplanets to highlight the fact that they are outside of the solar system. But they can be very different. They can be very different from the one we have in the solar system. So we can have very giant planets, several times the mass of Jupiter and very warm, or we can have planets quite close to Earth, for example, from the information we know. And so the difference between detecting and imaging exoplanets is very important because we will talk later about finding life. And so it's important to know for people who are listening that we already detected planets, terrestrial planets, rocky planets with possibly water on the surface. This has been detected, for example, and there's a very famous example of the TRAPPIST system that was discovered in 2015 by a Belgium team. So the TRAPPIST name comes from the beer, so that's how you know that it's a Belgium team of astronomers. And so they discovered a few exoplanets around this star in 2015. And in these exoplanets, 3 of them are actually in the habitable zone of the star. So what we call the habitable zone is the distance from the star where the water on the surface of the planet can stay as liquid. If the planet is too close from the star, then the water is evaporating. And if the planet is too far away, the water is freezing. So it's an important parameter for the habitability and the emergence of life as we know it. So planets that are potentially habitable have already been detected. But now the challenge today is how to image them. And so to image an exoplanet, we need to separate the light from the exoplanet and the light from the star. And that's the challenge today. That's what we're trying to do now in astronomy. And that has potentially a lot of very important benefits in terms of characterizing what is the atmosphere of these exoplanets, what is at the surface, and how habitable they are.
So would you say that detecting it is knowing that it's there, seeing it's out there and locating it, and imaging it is actually getting data from it and separating from the lights of the sun and things like going into more details? Is that right?
Yes, so detecting is the first phase.
Yeah.
Detecting is knowing that the planet is here, knowing how far from the sun it is, knowing how long it takes to orbit around the sun, around the star, sorry, but it only gives a limited amount of information because it is coupled to the light from the star. And thus it's a bit tricky to find what are the molecules that are in the atmosphere. Imaging is the best way we have to get as much information as we can.
And why is it so hard to image exoplanets? What are the challenges? So you've mentioned the light of the star, which I suppose is so much brighter than the planet itself. Are there other challenges you face?
So indeed, it is very faint. Exoplanets are much fainter than stars. They are from 1 million to 10 billion times fainter if we want to go to Earth-like exoplanets. But the second challenge I see is that they are also very close to the star, especially if we want to go to the ones that are in the habitable zone. They are very close, so we need instruments with very high precision to be able to distinguish the light from these points from the light from the star. And usually we made this analogy in astronomy. Detecting exoplanets is like trying to detect a firefly that would be flying around a lighthouse. So this is the most challenging part today, but it has a lot of benefits for the future.
And this is where your research comes in, because I understand you're testing out a new technique called nulling interferometry. So from what I've gathered, it's never been used in that context, but theoretically it could really provide some big improvements. So can you tell me a little bit about this technique and why it is so hard to implement and practice?
Yes, so it's been imagined in 1978 by an American astronomer, Ronald Bracewell, that imagined it for exoplanets detection. So it's not completely new. It has a bit of years before. The main advantage is that to tackle the two challenges we talked about, the fact that exoplanets are very faint and very close to star, the first solution is to get our telescopes bigger, to get a telescope as big as possible, to get as much light,
more light, right?
More light,
yes.
And also more precision over to distinguish between the planet and the star. But the problem is at some point, getting your telescope bigger and bigger, you have a lot of cost. It's getting very expensive. And also, we are also limited in terms of technology. At some point, we don't have the technology to do mirrors of 100-meter size. Right. Today, the biggest telescope that is being made is in Chile. It's the ELT, the Extremely Large Telescope.
Really? Is that the real name?
It is the real name. And this telescope, we have the biggest mirror for a telescope in the world that is 39-meter size. Okay. To give an order of magnitude, the size of the telescope is the size of the atomium that I just saw when I came here. The sizes are similar. And this is a problem because at some point, we want to send telescope to space because this gives very unique conditions for observing. And I don't know if you realize, but sending something as big as the atomium in space is unrealistic. And so this is where the method we're exploring is very important. It's to tackle the issues of detecting exoplanets. Instead of using bigger telescope, we use several telescopes with a smaller size. So imagine instead of sending the atomium to space, we would just send several telescopes like the Hubble Space Telescope, for example. We would send several of them and do like a constellation of this telescope. And using interferometry from several telescopes, just by combining the light in a very specific way, we can get the same performance as with a bigger telescope. So that's interferometry in general. It is being used right now in several observatories in the world, but on the ground. People are thinking and still exploring how to do it in space, but it's not done yet. And the technique you are talking, nulling interferometry, the one we're trying to implement, is a specific configuration for this different telescope. where we need the light from each telescope to be as symmetric as possible. So we call that coherency. We want the light from this telescope to be coherent. And so it means that we need to correct all the sources that can perturbate the light from another. For example, if the temperature of a telescope is slightly higher, if the pressure of the air is slightly higher or lower, we need to correct all the possible perturbation to get the light beams as symmetric as possible. And if we can, then by combining them in a very specific way, we can block the light from the star without blocking the light from the exoplanet. So we get to separate the light from the exoplanet from the light from the star. And if we manage to get the light as symmetric as possible, then we only increase the performance. Our instrument is as performance as we can get this light symmetric. So that's how powerful this technique is. And that's the big advantage, is that we can use this technique in space. And so you said, yeah, nulling interferometry is being performed in other observatories, but it has never been used before for exoplanets. The instrument we're making would be the first one to be used for exoplanets detection and exoplanets imaging.
I'll turn to you, Kaustubh, in a second, but I'm just curious, how far away are we, do you think, of actually implementing that new technique? Is it still science fiction, or are we getting on a technical level, you know?
So to implement it on Earth,
yes,
this has been implemented already.
Nulling interferometry?
Nulling interferometry has been used before, but not for exoplanets detection. So for exoplanets detection, this is what our instrument is aiming to do. So it's a matter of a few years now. Now the long-term challenge in the future is to do it in space. And that would give us the capacity to detect and characterize planets similar to the Earth.
Wow, a lot to look forward to. Kaustubh, you are a senior researcher and your work is at the intersection of astronomy and geoscience, which the first time I read it, I was a bit surprised. Those are not two areas of focus you're used to seeing together. But essentially, in the continuation of the conversation we're having, you're also looking to combine these to better study exoplanets. And when you joined KU Leuven recently, you had the mission to build a research group at this effect. Can you tell me about the focus of that research group?
Yes, thank you. Indeed, it is not common to think of astronomy and geosciences together. But I think recently it has been shown that to understand an exoplanet better, it's really important for people from the geoscience community and from the astronomy community to come together and work together. And this has been my focus since my PhD, to work on a thin line between astronomy and geosciences and to understand both parties, because both fields have evolved differently. Geoscience has a lot of data, especially focused on Earth, on different aspects. Astronomy has little data, but potential for a lot of statistics in the future with the help of detections of now 5,000 exoplanets and probably tens of thousands in the near future. So I joined KU Leuven and the Royal Observatory to build a research team to work on this topic, and especially we'll be focusing on exoplanet interior atmosphere interactions. We will be doing laboratory experiments to understand how, for example, rocks and gases interact. This kind of information is vital because the atmospheres of exoplanets are influenced by how gases are outgassed from the interior. There are processes like outgassing, ingassing, then geochemical cycling, which can influence the atmospheric composition. And our focus would be then to further simulate, with the help of computer simulations, the atmospheres on the basis of the lab data we obtain.
Okay. So I was reading a specific paper that you co-wrote, Diverse Carbonates in Exoplanets Oceans Promote the Carbon Cycle. So I read through it. I tried my best to understand it, even though a lot of the words were very technical. Can you tell me what this was about and what you were trying to answer in writing this paper?
Yeah. That's related to the geochemical cycling I was talking about. Inorganic carbon cycle is a type of geochemical cycle which allows the cycling of carbon between different reservoirs on Earth, and it is thought to be an important process on Earth to maintain temperate climates for billions of years. And on modern Earth, we know that there are several steps for the carbon cycle. Out of these steps, two important ones are the weathering of silicate rocks and the ocean floor precipitation of carbonate rocks. And in this particular paper, we tried to explore the ocean chemistry and carbonate precipitation for diverse carbonates. On modern Earth, we focus on calcium carbonates. What we did in this paper, we tried to look into two different type of carbonate systems, and we found that they can also be potentially helpful for the carbon cycle, even if calcium carbonates are not present. So in principle, what we try to address here is the fact that chemically different systems from that of Earth can also maintain temperate climates.
Mm-hmm. I really like that because actually it brings me back to high school and something we studied. So it makes a nice bridge because I remember talking about, so you talk about the carbonate cycle, inorganic carbonate cycle, carbon cycle, sorry. And so how rocks evolve, they go from silicate rocks, I think, so quartz, olivine, and then turn to carbonate rocks. And we have sedimentation and then back through volcanism. So it's a whole cycle that, as you said, is on Earth as well. So we're familiar with it. But then what you just told me, if I understood correctly, is that the chemical diversity will promote that cycle. And that might influence the search for life, because we've been looking at Earth twins. So Earths that are very similar on a chemical level. But you're saying maybe that's a mistake and we should look at other planets that don't have the same chemical composition, and we might be surprised by what we find there. Is that correct?
So what currently the search for Earth twins relies on is they are looking for planets at a distance similar to the Earth-Sun distance around the host star, and
so
also
the habitable zone that Germain was talking about, right?
Absolutely.
Mm-hmm.
And within that habitable zone, then the planet size is similar to that of Earth. With the help of this study, we try to demonstrate that one should also look for chemical systems which are different. So this is also not something absolutely new. This has been a part of discussion in the last 5 years in the exoplanet literature, that we should also look for chemically diverse targets. But with the help of this paper, we demonstrated again that even for geochemical cycling, this might be an important aspect that we should not miss out on when we define the chemical, the Earth twins, which could be physically similar but not chemically similar. So
right, that makes sense. Okay, I'd like to go back to a more of a general perspective on the work that both of you do. Everything we know from these exoplanets, we know literally from a distance, right? So we cannot go there, we cannot get samples, we just can look. So
for now,
for now, that's true. For now. So your work is to make sure that we get a light in a detailed enough way that we can actually interpret it. And your work is to interpret it. If I vulgarize it to a large extent, but that's the idea.
Yeah, that's correct.
And my question is, how can we have information? Can we have data from a tiny little point of light? What can we know about planets through light? What are the techniques you use to turn, I suppose, the color of the lights to information? Both of you, whoever wants to jump in.
Yeah, so the imaging technique which Germain mentioned, it's very important because you can imagine if you collect a lot of photons from the star, what one can do then is use that to split the light, like in a prism. You can split the light in a rainbow. And the same thing you can do if you collect a lot of photons from the star or the planet. And this allows you to look at something we call spectral lines. So these are dark lines within this rainbow, which can then tell you that, okay, this particular molecule is present in that planet. And this is a very, very vital information, that this particular line or this particular molecule is actually present. And this has been already done since last two decades almost. And now the challenge is to go for smaller planets closer in, with direct imaging. And of course, there are some alternate techniques as well, where you can look at the transmission or emission spectra when a planet passes in front of the star. So these planets could be very close to the star, much closer than direct imaging can do. So this is a complementary technique.
Right.
Maybe I can add,
Yes.
a reason why we want to go to space is that some part of the light that is coming from stars and exoplanets is not transmitted by Earth's atmosphere. It is being absorbed. And so we lose this information that is potentially very rich in information about what kind of molecules. We know that, for example, water and CO2 have a lot of this spectral information in the infrared in a part of the light that is not transmitted by the Earth atmosphere. So that's another reason why the launch of the James Webb Space Telescope was a very big news, a very good news in astronomy, because then it was able to get the spectrum and get information that was not possible to get from Earth.
So if I understand correctly what spectroscopy is, it's basically as if you were using photographic filters, like a red filter. So you know a certain molecule is going to hide out red. And when you receive the color, it's not quite white light. You notice the red is gone, so you understand the molecule was there. But what you just said is that the atmosphere of the Earth also has that effect. So there's a filter at the input source, but also just before we receive
Yes.
it. So we'll get a more detailed spectroscopy once we manage to put those optical instruments in space, such as the James Webb Telescope. That's very exciting, and I guess it takes us one step closer, because you mentioned water. Immediately, that makes me think of life and the search of life. Can I ask your instinct? What does it tell you? Is there life out there? And if so, will we find it? Is there close enough life that we could find it one day?
I think the question, so there is something we have in astronomy a lot of years ago. There was an astronomer who made this Drake equation. It's like a very simple model to try to estimate in our galaxy how many planets are habitable, how many have intelligent species, and in how many can we actually detect signs of technology of an intelligent species. So it's a very rough model, and a lot of people are criticizing the results. But the number he found was that in our galaxy, he was estimating that around 20 planets would be potentially habitable and inhabited by intelligent species, including Earth.
So 19
obviously.
others to find.
So potentially 19 other. So I think, yes, I think it's quite likely that that life exists somewhere in the universe, and maybe somewhere in our galaxy. At least we don't have any information that would prevent life. We don't have any news that life could not appear on other planets. But I think the question now is, if life exists, can we find it in the planets that are in the neighborhood of Earth? Because we are not able to detect and characterize all the planets in our galaxy. We can actually only reach the planets from the stars that are in our neighborhood. So now we need to try to find for a habitable planet and potentially life in these planets. And is there a planet with life that is not so far away from us, so that we can detect it and so that we can find it?
Do you think it's there?
Yeah, I mean, I came to this field really from outside. I was fascinated by just the talk of exoplanets, and I then jumped into this study of astronomy, and then I'm really glad I can continue doing this. So at that time, I naively thought, yes, of course there must be life, but now with the help of 10 years of being in this field, I still now think the same. But then I have a little bit of evidence to back me up in terms of statistics, because you can just see in our galaxy, the estimated number of stars are about 200, 300 billion. Estimated planets are about 1 trillion. And in the universe, the estimates for number of galaxies is also between 100 billion to 1 trillion. So 1 trillion times 1 trillion is 1 septillion. I looked it up. So there are so many exoplanets possible. Of course, the ones we will ever be able to really do something about are the ones in our own galaxy. And this has been probably this will be the focus. But having said that, we should also not only think about exoplanets as the places to find life. We should also think of planetary bodies in the solar system, especially the moons in the outer solar system. And talking about that, European Space Agency is launching a mission as we speak. And by the time this episode comes out, it might be already flying towards Jupiter.
Really? Do you know more about this mission? Can you tell us about it?
I'm not directly involved in this, but I know from my colleagues that this is going to be a big mission to the icy moons of the Jupiter. And it's going to find a lot of interesting things which we did not expect.
I've actually heard about this because they made a little challenge on Twitter. I don't know if you've seen this, where they ask people to represent icy moon as so people, I think in a cocktail or in a drink or something like this. And I saw some tweets about this. It looked really fun. But so we mentioned water and markers for life. Can you tell me I was asking about your instinct, but on a more scientific level, what is the strategy for people whose job is to look for life, for this part of the science community? What is the strategy to look for life in the universe? What do you look for specifically?
I think so. The first step is not done by me. You can say the first step is done by biologists and chemists. It is to find what is the information that we can try to find on a planet, and that would say that this planet is potentially habitable and potentially inhabited by some species. And so you mentioned, we mentioned water and CO2, for example. So these molecules and elements are necessary for the emergence of life as we know it. Every time we say life, we should add as we know it. Life as we know it needs oxygen and water, for example. But we know that these molecules are not a proof that life exists. For example, on Venus or Mars, there was water back in the days, there was water and oxygen, but it doesn't make these planets habitable. So we need to find, the scientists, biologists and chemists need to find what is the molecule that is the best proof that life is on this planet. And for now, so I asked a few of my colleagues that are more expert on the subject than me, and they told me that for now, the best candidate is ozone, the ozone gas, coupled with methane. So if we manage to find ozone gas and methane on a planet that is potentially habitable, then we have an idea of that, yes, potentially this planet can be habitable, can be inhabited, yes. So that's the first step to find something. The second step is now my responsibility, I can say, is to find a way to observe it, because it's good to know that ozone is maybe a proof that life exists, but we need to be able to detect it. And so that's the second step, finding engineers, astronomers to develop instruments to be able to detect it. And I think the third step is when we manage to get instruments, when we manage to make the observation and to detect these molecules on the planet, now we send this data back to chemists and biologists, and then they need to try to understand what is going on the planet. From this information, what can we deduce from the conditions, the habitability of the planet? And this is, like you said, this is a circle of information. The information is going back to biologists that are developing models, theories, and then it's coming back to astronomers to try to find new instruments and find new information that can try to make us reach the truth about life.
That's so interesting that you use the word circle, because in preparing this episode, what I wanted to highlight was that the scientific community is a chain where information goes from one person to another, with everybody having their own expertise. But what you're pointing at is, indeed, it's a circle, because you start at a point, you get information, you know what to look for. Once you've found it or not found it, you go back to the first people, and there's this constant emulsion of ideas and feedback. It's so interesting. It's very precious, and I'm glad to close this first season with you guys to sort of highlight that part of the work. We've talked in previous episodes. We've talked to people who focus on politics and legal sides of things, who focus almost also on the philosophy. But at the really ground level, we need the instruments and we need the science to make things make sense of what we found. Maybe as the last question, because I know, Germain, we've talked about this before, but this often is the sentiment in space in general, that the USA is doing everything and it's the big leader and nobody else exists, which is not quite true, at least not in every aspect, especially not for science, I think, and what we call, I believe, blue sky science. I know in French we say recherche fondamentale, so the primary research, the sort of research that doesn't have a clearly defined goal, which is trying to gather information and knowledge. Do you have examples of achievements that would have come out of Europe and its various institutions, such as the ESO? Can you tell me a little bit about the ESO?
Yeah, so I can only talk about my fields. And I think the point is not to say that we are the best and that which one is the best between the USA and Europe. But definitely in terms of what we call ground-based astronomy, definitely, I think Europe has very interesting facilities, and you mentioned ESO, but even before the creation of ESO, or maybe it was created at the time, I forgot, but a number of Nobel Prizes were given to European researchers or for European institutes. So, for example, the first exoplanet that was detected in 1995 was done in France by Michel Mayor and Didier Queloz, and it was the Nobel Prize of Physics in 2019. Also, the Nobel Prize of Physics in 2020 was done thanks to an instrument of ESO, so the European Southern Observatory, who is one of the biggest observatory in the world, that is located in Chile. And in this observatory, there is an instrument that is called Gravity. And this Gravity instrument was the first one that was able to detect the supermassive black hole that is at the center of our galaxy. And this resulted in the Nobel Prize of 2020. And so I think we have a lot of facilities in Europe. So ESO, the European Southern Observatory, is also building the biggest telescopes that I mentioned a bit earlier. The ELT is also being built at ESO, so it will be a European facility. And I was talking about interferometry, that is a very promising method. Well, the ESO also have the VLTI, that is a very large telescope interferometer, that is also a very important facility for this field, very advanced. And I can even say that in terms of interferometry for exoplanets detection, I think we are even a bit in advance compared to the USA, because the USA right now is starting to build their interferometers, but we already have a few of them in Europe. So I think in terms of exoplanets detection, in terms of ground-based observation, Europe is definitely a leader in many projects, and is also with ESA. ESA is also leading a lot of projects to space. So I think the European Union is also definitely having very important, and some of my colleagues are working on space missions that are 100% European. But it's always difficult in research. Research is a lot of collaboration. So we can't really say that this is completely European, this is completely American. This is a lot of collaboration. But I think the point I want to make is that the European Union is not dependent on the USA. The European Union is leading a lot of very important, very interesting projects in astronomy.
That's great to hear. Thank you both so much. This was really interesting. As I said before, I'm really glad we are wrapping up this first season with you two. For now, I would like to thank you all for following the program, and once again to thank Tom, Sean, and Andy, without which this 5th episode would never have happened. I look forward to seeing you soon for a second season, maybe. And before that, let me remind you, we'll be hosting the Making Space Matter Summit on June 6th. You can find more information on our website and look forward to talking to you soon. Thank you so much.